We're going to talk today about ferrous metals. So ferrous metals, as the name implies, if you're familiar with the atomic symbol for iron, you know that it's Fe, and that comes from the Latin ferrum, which means iron. So these are elements, or not elements, these are alloys that are primarily iron-based. So they have, as a major constituent, iron. There are some non-ferrous alloys, I will say, that have a little bit of iron in them as an alloying element. Those would not count as ferrous metals. These are the ones that are primarily iron-based. All right, so this lecture assumes that you've had Tech 1711, and if you have not, I have put in here links out to the lectures from 1711 that are relevant to our discussion today. So if you got in this class and have not had this background information, I will go over it really briefly here. But if it gets confusing to you, I would recommend that you watch these from start to finish to kind of get up to speed. So just really briefly, I'm going to back out here to 1711. To understand ferrous metals, we need to make sure that you understand kind of just the background information on what a metal is. And so I'm going to just kind of fly through this. Remember that metals are that category of elements that really like to give up electrons, and so that giving away of the electrons in their outer shells is what makes metals behave the way that they do. And most metals, for the most part, at least in their pure state, will behave really in very similar ways. They're very ductile, they're malleable, they tend to conduct electricity, and all of this has to do with the fact that they like to shed out those outer electrons. Some of those do that really dramatically, like the alkali metals. So I'm not going to go into all of these today because we are only concerned about one type of alloy, and that is the iron-based alloys: steel, cast iron, stainless steels, things like that. But really quickly, make sure that you understand that giving up of the electrons is the way that metals are able to bond to each other. This is not an ionic bond, it's not a covalent bond, it's its own type of bond. Okay, since all of these metals have decided to give up their outside electrons, then they can share those freely. And since they are not attached to those electrons, they take on a positive charge. And you might think, well, all these positive charges, they should repel each other, except they're drawn together by this sea of shared electrons. And since none of these electrons belong to any atom or metal ion in particular, they are free to move about and flow through here. And in fact, if we apply a really strong force to this, we can shift these rows of atoms past each other and do plastic deformation on these metals, and they will remain bonded together, just as bonded as they were at the beginning, until things like some discontinuity start to propagate through, and you start to get some failure action in there. But there's a wide area where you can do plastic deformation on most metals, and they will flow. They're very ductile. I'm not going to camp out too much on the lattice structures, although we could, because that kind of becomes important when we're talking about stainless steels, but we're not going to really get into things like stainless steel selection and things like that. I'm certainly not going to go over the stress strain diagram again because you've done plenty of that in this class already. I will drop down here, and this is the iron-carbon system. So this lecture would have begun with a slide that looks like this. Hopefully to most of you this looks really familiar. To some of you this may not be familiar, and to those of you who don't know what the heck that is, I would say come back out and watch the phase diagrams video and get up to speed on that. All right, so I'm going to start the discussion of ferrous metals by saying that, first of all, this is sort of the backbone of the ferrous metals. This is simply the iron-carbon system. Now, a lot of, if we talk about alloy steels or stainless steels, then we are certainly adding other alloying elements besides carbon. But this is the beginning point to understanding what's going on with these ferrous metals. First great big main idea is that to the left of this point right here, where we have this gamma, this you'll remember is austenite. So this austenite region out here is all of, if we can do this to the steel or to the iron carbon alloy, then we'll call it steel. If we cannot do that to the iron carbon system, if we have too much carbon in there, if we're to the right of this point, then we're going to call these cast irons. Okay, so that's the first main big distinction between steel and cast iron. There you go. So if we're talking about stainless steel or something like that, then we're on this side. If we're on this other side, we're talking about gray iron or white iron, then we're on the cast iron side. All right, again, it's going to be important that you remember these things: ferrite, austenite, cementite, and later in the heat treating section we talk about martensite. Okay, so I'll just refresh your memory a little bit. The ferrite exists in here, and it is body-centered cubic, and it does not like to you can't really dissolve very much carbon in it, as you can see plainly on this diagram. Okay, so ferrite is not going to allow much carbon to dissolve into its structure. However, austenite will. So here we can pump an awful lot of carbon into austenite. You can see we get out here almost to 2% if we get it just the right temperature. But austenite is this face-centered cubic structure. So that exists here. Over here we have ferrite and cementite, and we have those layered together. And we said that what we get if we heat treat, or if we cool slowly enough, we wind up with a pearlite structure like we see here. One other microstructure that I'll mention is martensite, and you'll remember that we get martensite if we have enough carbon in the steel and then we cool it quickly. Okay, so if we quench that steel down, cool it quickly, which takes us off of this. This is an equilibrium phase diagram. We would have to be looking at a time temperature transformation diagram to be talking about martensite. Okay, so that is the really quick review for those of you that remember those things from Tech 1711. If you don't, like I said, there are links to those lectures. All right, so these are the main groups of ferrous metals that we'll talk about. We'll talk about steels first of all, and we can see that we can start to break steel down, and then if we add enough chromium, then so steels could be carbon steel, or they can be alloy steels, and if we add enough of a particular alloy, and that is chromium, then we wind up in this group of steels called stainless steels. Then there's a group of steel called tool steels, and these are various alloy steels that are fine-tuned to certain for certain applications, generally tooling applications. And then we'll end up just going over the cast irons really briefly. All right, so first of all, steel. You can make steel with nothing more than iron and carbon. So you can have, that would be a plain carbon steel. That's what that iron carbon system diagram would be showing, would be just a plain carbon steel. So it can be, a steel can be classified as a carbon steel even if it has a certain amount, it's very rare unless you're doing some kind of laboratory work or something that you would have zero other elements besides carbon and iron in a steel. And so certain levels of these alloying elements are allowed. Some of them, are going to be detrimental to the steel. Some of them tend to improve the steel. But then, as I said, as you add more and more of those different alloys, you'll wind up with something in a category called alloy steels. Now, I'm just going to mention at this slide right here that as we talk about really all of these materials, the steels, the stainless steels, the cast irons, don't expect that you can just get any shaped material like a piece of tubing or a piece of pipe or a round tube or a rectangular tube or a piece of sheet steel in any of these materials. Okay, so a lot of these materials are kind of fine-tuned for certain applications, and so in those applications it might be that you can only get round bar stock for a particular material. So always be in touch with potential suppliers, check catalogs, find out, before you go out and spend a lot of time specifying a material, make sure that the shape that you need that material to be in, that you can get that shape in that particular alloy. So it's kind of a balancing act. You have, do you need a bar shape? Do you need a round bar, rectangular bar? It might first be that you know that you need the bar, and then you're going to have particular alloys that you can choose from. Some, you generally want one that's already in production, unless you're going to be buying, millions of pounds of the thing a year or more. So just understand that that's not all steels, or really all ferrous metals, are available in all of these different in any shape that you would want. All right, so let's talk about buying some steel. And I guess I really mean specifying a particular steel. There are various agencies that have designations and specifications, standardized specifications for steels. The most common are these, SAE and ASTM. At least in our country, those are the most common. So you may be familiar with the 4-digit SAE, formerly the AISI SAE 4-digit designation system for steels. We'll break that down, review that a little bit in just a minute. Then there's also, there are ASTM standards for various steels, okay? And then there are German standards, European standards, and there is this thing called the UNS, which is essentially a cross-reference. So you can order steels based on this UNS. Generally, that's if you're doing international trade. So, this is the American Society for Testing Materials. It is not, even though it's widely adopted internationally, it's not adopted exclusively internationally. And so, to be able to tie together some of these different standards, the UNS system will cross-reference those different specifications. All right, the steel industry as a whole uses these three terms in a specific way. Okay, grade, type, and class. If they're talking about the grade, and this is the steel industry, if the steel industry or someone in the steel industry is talking about grade, they're talking about chemical composition. If they're talking about type, it's the deoxidation practice. And if they're talking about class, it's some other characteristic, okay, like strength or surface smoothness or grain size, things like that. But keep in mind, ASTM is more broad than just steels. It's all kinds of materials, and so you will see ASTM use those terms differently. So don't just lock in on these. Just be aware that with ASTM, these are not always adopted consistently. All right, so there are these. There are, first of all, the simplest of the steels. These are the carbon steels, and these are broken down into low, medium, and high carbon steels. Generally, you'll use a low carbon steel when you want something that's nice and easily formable, and you start adding carbon as you need more strength and heat treatability in the steel. Now, it is really common when you're looking at these steels to see them categorized kind of by the process used to make them. All right, so there are rimmed steels, capped, semi-killed, and killed. I am not going to go into that. I do have a link out here to a pretty good explanation of what that means. But in general, you talk about steels almost plant by plant. This particular plant does this kind of steel and another type. And so, anyway, that is a categorization that you will sometimes see on the steel. All right, if you take those carbon steels and you start adding, in particular, manganese, silicon, and copper, then you will shift. If you add enough of these, you will shift and become what's called an alloy steel, or your steel will become that. You won't become that, but you'll then have an alloy steel. So these are the common alloying elements in the steels. So carbon, of course, they're going to have carbon, or it wouldn't be steel without it. It would be pure iron, which is, well, I'm not going to go there. You can also add very commonly manganese. So manganese is a lot of times added to improve the mechanical properties of the steel. So you can get better strength and hardness, and hardenability and resistance to wear by adding manganese. Nickel, We'll look at nickel in a little bit more detail when we start looking at stainless steels and also chromium. But these two can increase the strength and also the corrosion resistance. And of course, that's when, that's where they really start to shine. Sorry about the pun. When you go to add these in larger quantities in stainless steels. All right. But these are the most common sorts of alloying elements that you will find in steels. All right, so this should hopefully be a little bit familiar to you, so I'm not going to beat it to death. But this is that SAE steel, these SAE steel grades, okay? And so this is an example of a standardized specification. If you ask for a particular SAE steel like 4140, when you're asking for that, there is a standard written out for this particular steel, and you can go out and check SAE. This is an example of of an SAE standard that is referenced by calling out this particular number. So in the SAE system, this first digit is the major alloy group. Okay, so example, the carbon steels, I broke these out a little bit more, but the carbon steels all start with a 1 in the very first column here. This is an example of a molybdenum steel, and more commonly it would be called a chromoly steel because it's a chromium molybdenum alloy. All right, so the 4 places it in the molybdenum steels, and the 41 makes it a chromoly. So any of these could be broken out. There's many more subcategories in here. I just started breaking out the 1000 there, but it'd be hard to read it on a slide if I broke them all out completely. Then the second part of this is the carbon content. Okay, so this is not 40% carbon. A lot of people get confused sometimes. They see, one way to talk about 40% would be to say 0.4, okay, because 0.4 would be 40%, but this is not 0.4. This is not 0.4. It's 0.4%. But hopefully you'll just think about this. This is generally going to be less than 1, okay? If it's greater than 1, then they'll pop another digit in this sequence here. But remember, 2%, if it's anything above 2%, it's not even steel. So don't think this is 4% or 40%. This is 0.4% carbon content. All right, so in addition to the SAE standards, there are the ASTM standards, okay? And so a lot of times, for like building and construction, this I-beam, a lot of this stuff, it has nothing to do with automotive engineering. I will say the reason that this is so popular is because, there are so many mechanical functioning parts on an automobile that if it's on a car, then there's probably, if that steel is being used on a car, then there are probably lots of other applications where that steel would be useful. One of those would not be building and construction. Okay, so if you have if you're designing buildings or bridges or things like that, it's very common to ask for this stuff, ASTM A36. This is a separate, not related to SAE at all, but a separate standard, in this case, for structural steels. And I did put a link up to the ASTM A36 standard, so you can take a look at that on the course module for this lecture. So if you're asking for A36 steel, then inside that standard, it's going to tell you the chemical requirements. So it's going to have the maximum amount of carbon and phosphorus, things like that. It also asks that the steel be a killed steel, and that is a fully deoxidized steel, and that it will also have to have certain mechanical properties. It'll have to have a certain tensile strength, a minimum tensile strength, a minimum yield point, and the minimum elongation. It has to have ductility requirements. And there's some other things in there. The shape of this particular I-beam section would have come from a separate standard. So that would come from this ASTM A6. All right. So the different standards specify different aspects of that steel product. All right. There are steel products that you can buy that are completely standardized. So there's things like socket head cap screws. You can get ASTM A574 socket head cap screws, and that standard will specify everything about the chemical composition, the mechanical properties, workmanship, finish, and everything about this, because it's so, it's a very specialized application. There's only so many uses for socket head cap screws. Of course, there are socket head cap screws besides these. You can get titanium socket head cap screws and even plastic ones and things like that. But this is a nice, common, easily purchased, consistent standard, and you can buy this and know exactly what's going into your socket head cap screws. The dimensional requirements for those are specified separately, sort of similar to with the I-beam. All right, there are other standard specifications out there. For instance, there are a lot of mil specs, and sometimes these will reference ASTM standards, sometimes not. But there are mil specs, or ISO standards, British standards, German standards, Japanese standards, European standards, and also you'll sometimes see steels specified by a trademark or trade name, like this AR500 is a fairly commonly used armor plating steel, but that's a trademark. So it's like Armor AR500 is the trademark, and they get that actually, just interestingly, from the Burnell hardness of that steel. It has to have a Burnell hardness of 500, within a range of around 500. All right, another way that you'll see steels categorized is by these things called quality descriptors. This is a very, very, very partial list, just to give you an idea of some of the quality descriptors that are out there. But in general, this is kind of the way that you'll talk about a particular steel mill. You'll say, well, that one's making bearing quality alloy steel wire, okay? And that's just a nice general way to talk about the type of steel that's going to be used for a specific purpose. All right, so a lot of times you'll see steels manufactured not just for a particular industry, but for a particular place within that industry. Like here, axle shaft quality hot rolled carbon steel bars. Okay, so sometimes this is a way to shop for steels that might be being mass produced, but you might not see them from your steel supplier. But this might be something that you could go after, is by looking for steels under particular quality descriptors. All right, so then we said that if you start to add chromium, then you'll turn your steel into stainless steel. So you'll see a lot of the time that this number, 11% chromium, is the magic number to start talking about stainless steels. I will say there are some stainless steels with less than 11%, and some books will say 10% chromium will make a stainless steel. But I think it's a little more common to see 11%. But like I said, there are some that are have lower than 11% chromium. But in general, it's a good rule. So these are the main classifications of stainless steels, okay? And this is one reason that I went all the way back and started talking about austenite and ferrite and martensite, is because you see those here in these stainless steel structures. And just understanding what austenite is and what ferrite is and what martensite is will go a long way to kind of helping you understand what's going on with these stainless steels. Now, I'll just back out and say that as a general rule, stainless steels are more expensive and harder to work with than most steels. Okay, so generally you'll only use a stainless steel if there's some kind of an appearance or a chemical compatibility requirement, or some other requirement that the material be stainless steel. Okay, so maybe magnetic properties or things like that. So, you can get an austenitic stainless steel, that will be non-magnetic. Okay, and also, it won't heat treat. And the reason is, it's this austenite structure. Okay, well, let me not dip into that too quickly here. Okay, because I'm just going to say that a lot of times you'll be trying to specify a stainless steel. You'll be doing that because you have to generally, and what you're going to have to balance are the mechanical properties of that material, the cost of that material, how well it's going to stand up in the environment where it's going to be in service, and also can you make it that way? The process requirements, because a lot of times stainless steel is going to be more difficult to machine, more difficult to form in general, just as a general rule, than a lot of other steels would be. Okay, so I'm going to move forward on this to kind of break these down, but just keep in mind that you should know what austenite is, what ferrite is, what martensite is, to really understand what's going on here. So if you understand those things, then this is kind of the key, okay? One of the keys is that nickel will stabilize austenite, all right? So this, I'm going to bring you back. I actually pulled this out of the 1711 lecture, and remember that if you add nickel, it starts to drive down this eutectoid temperature. What that means is that this eutectoid point, if we start to add nickel to this diagram, this thing is going to drop down. Okay, so, and if you add enough nickel, you'll drop that thing clear down to room temperature, and you'll stabilize this austenite form, which is non-magnetic, and it's also not going to be heat treatable. Okay, so that's your austenitic stainless steels. And you can see this on the diagram. Okay, so this, I love this little diagram because it really says so much about the stainless steels. Okay, and that is, there are two main alloying elements that you'll see in stainless, and that is chromium. And we see chromium on this axis, and of course here we see nothing below 11% except this oddball, this 501 or 502 heat-resisting steel over here. But in general, we've got everything is above 11% chromium, and then some of these have nickel, some of them don't. Notice as you start to add nickel, what do you get? Well, you get, for the most part, you get these austenitic stainless steels. So adding nickel takes you into the austenitic zone. Now, over here we've added nickel, but we are in between a ferritic structure and an austenitic structure. These are called the duplex stainlesses, and it's the remaining elements that we're not talking about that makes the difference here. So you see that these compete with each other. That means that we can stabilize the austenite, or we can add nickel and add something else to prevent that nickel from stabilizing. Notice that chromium does that. As we move further out here, then we can add more and more nickel without jumping back up here into the austenite region. That nickel, or that chromium, will help to kind of compete against the nickel to pull that eutectoid temperature up and prevent the austenite from stabilizing. And you can get a mix of the characteristics of ferrite and austenite inside of this duplex stainless. Then you see down here at the bottom, with low nickel content, are the ferritic stainless steels, and we see some overlap here with the martensitic stainless steels. All right, and based on what you know about martensite, what do you have to have for martensite to form? Well, you have to have carbon. Okay, so the big difference there is primarily the carbon content, and you wind up with these martensitic stainless steels that can be heat treated. And then there's this one more oddball in here, this 17-4. That is a precipitation hardening martensitic stainless steel. So that one can be hardened by a precipitation hardening process. And it's, well, let me drop down here. Most of these are designated by at least a 3-digit number. Okay, so this is an SAE classification, and sometimes you'll see additional letters behind those numbers out there. Okay, so they are generally they do generally follow some pattern, but if you look at this, it's like, well, there's a 300 and there's a 200 there. They're both austenitic. Over here we've got both ferritic and martensitic are both 400 series. So unfortunately, you can't just look at the number and know by looking at the number unless you have it memorized whether it's ferritic or martensitic stainless steel. But this is kind of where those groups lie on that diagram. All right, and then finally we'll talk about the tool steels. I mean, finally, in terms of steels, we'll still cover cast iron here in a second. But the tool steels are really a great way to buy a steel for a specific purpose. Okay, so if generally these are tooling purposes. That's the reason I've bought these in general. But they're really good high-performance steels designed for demanding specific applications. And so that's how you'll see them categorized. To a certain degree, you'll see them categorized by how the hardening or quenching media that they're used with, like O for oil hardening, A for air hardening. But these all together are kind of the cold work group. So all of the O series, the A series, the D series, these are really good for doing things like punching and drawing dies and things like that. The shock resisting tool steels, the S series, and I should say most, these will come with a letter or a number that follows these letters, like O1 or A2 or D2 tool steels, or H13. Okay, but these are they break down by category. So shock resisting tool steels tend to be very, very tough. Okay, and then the high speed steels are also sort of, this was the original sort of tool steels, and there's the M type and the W type. Scratch that. It's the M or T type. I'm not sure. I think my brain just did that because it is the molybdenum series and the tungsten series. Okay, and of course the atomic symbol for tungsten is W, but as far as tool steels are concerned, it's M or T. Then there are the hot work steels and mold steels. Okay, think plastic when you see the P there. This is a really good link if you go out and click on that for sort of seeing how you can figure out which tool steel is better for your application. Okay, because generally it's a trade-off of these three things: the toughness and the wear resistance or hardness, and then how easily ground it is. So the grindability. Most tooling is made by machining, heat treating, and grinding operations. All right, but this just shows you that that you can get a steel that fits a specific application. All right, and then finally we'll talk about cast iron. So cast iron, as we said, is this iron steel alloy that has greater than 2% carbon, and we get different behavior, different property out of the cast iron. Let me just drop back up to our diagram one more time. And you see that one thing that adding all of this carbon does is it will eventually drop the melting point down a little bit. All right. But in general, speaking about cast irons, they tend to be made by casting, first of all. Of course, you can machine them second after you've cast them. So it's very common to cast a cast iron part and then machine in the surfaces where you need precision. So think of like a machine bed, like the bed of a lathe, a lot of times made out of cast iron. And then certain surfaces can then even be heat treated and machined, or ground, or machined. But cast iron tends to be brittle. You tend to be able to machine it without coolant. It is possible to machine cast iron with coolant. In fact, there's a company locally that does an awful lot of machining of cast iron, and they actually use coolant with that cast iron. But anyway, the major categories are gray, white, malleable, and ductile iron. So this sounds like kind of the same thing. But anyway, we'll start with gray iron. So gray iron has enough carbon in it that the carbon actually precipitates out as graphite, and so with the gray that you see are the graphite flakes. White iron actually has all of the iron all of the carbon dissolved into the microstructure in the form of cementite. And then malleable iron is essentially white iron that has then been heat treated to allow some of that retained carbon that's trapped in the cementite to precipitate out. Same thing with ductile iron, as you have the graphite exists in ductile iron in little nodules. Okay, so think about when we talked about spheroidizing steel, sort of the same idea here, where you have the carbon precipitated out into those round spheroids. All right, but that's the main sort of introduction to ferrous metals, and we'll talk more about some of these metals as we talk about processes. Okay, so maybe we'll talk about deep drawing, for instance, and how there are certain metals that are more that are better suited to deep drawing applications than others. So, but this is the lay of the land. That's all for today.